All right, these notes, this video is for notes for section 6.2, and we're finally getting to the point where we're really officially talking about the unit circle. I think I probably have mentioned unit circle occasionally in other previous lessons, but here we're going to get to sort of a true explanation of what unit circle is and how it can sometimes simplify some of our formulas. Okay, so a unit circle is just a circle whose radius is 1. That means the circle intersects the x-axis at a point here, which is 1, 0. Up here, it intersects the y-axis at 0, 1. Intersects the x-axis on the left here in the negative x axis at negative 1, 0. And then down here, the circle intersects the y-axis at 0, negative 1. Okay. So first, when we do unit circle, if we think about it, the r is 1. So what we learned in the last unit about arc length, our arc length is r times theta. Of course, again, assuming theta is in radians. So if we're on the unit circle, then the arc length and the theta are really the same. Okay, so that instead of saying what is the sine of an angle, we can say what is the sine of the arc length, because if and only if we are on we're on the unit circle. Okay, we know that x squared plus y squared is equal to r squared. You know, that's if we were to sort of draw a right triangle here, right? We know the x for this point, the x coordinate, the y coordinate, and the r, we could square those, right? Square x squared plus y squared was equal to r squared. But now that simplifies things a little bit too, because r is 1, so x squared plus y squared is equal to 1. All right, so instead of theta, we're saying s here, but you know, that's really the same thing as theta since we're on the unit circle. But since we're on the unit circle, r is 1, so that means the sine of the angle, or in this case the arc length, is just y. Cosine is just x. You know, it's x over r, but again, x over r, x over 1, just x. Okay? So that simplifies things. So sine, you should be always thinking about it being y. Cosine of the angle, you should always be thinking of x. And of course, cosecant would just be 1 over y, secant 1 over x, tangents still y over x. That doesn't really change here, but because there's no r's in these ratios, but it does simplify things a little bit. Okay, this unit circle, so this is, assuming this is a unit circle, this looks a lot like the thing we filled out with the common angles, both in degrees and radians in the last section, in section 6.1. But here, what we're adding to it is the coordinates of this point, assuming we're on, of course, the unit circle. So this point, like we said before, is 1, 0. This point is located at square root of 3 over 2, comma 1/2. And so we don't expect you to memorize these. You know, some people do, and with enough practice, you kind of sort of know what they are. But ultimately, in most cases, we're going to draw a little right triangle. So if I say pi over 6 is our angle, so if this is pi over 6, then we think about this right triangle, and we say, okay, pi over 6, that's going to be 1, 2, square root of 3. On the unit circle, this would be 1. This will be 1/2, and this will be square root of 3 over 2, 1/2 of square root of 3. Okay, so so if you use these, remember we don't have to always use the unit circle. It just depends on the circumstances. Sometimes using the unit circle makes things simpler. All right, let's see what else. Since this is the unit circle, the coordinates listed are also the cosine and the sine. So that is, right, since we're on the unit circle, the cosine of 60 degrees, cosine of 30 degrees is our x, square root of 3 over 2. the sine of 30 degrees is 1/2. So these things don't only give us the coordinates, but remember, they give us the sine and the cosine as well of that angle. Okay. Also notice that the cosine is restricted to 1 and -1 because the x fluctuates as we rotate through angles, right? We just keep rotating. We'll go from 1 to -1 to 1, -1, and we'll oscillate. So the lowest that the cosine of an angle can be is -1. The highest it can be is 1, and the same thing for sine. Just know that for the sine, the maximum occurs up here and the minimum, -1, occurs down there. Okay. Domains, sometimes it's helpful to think about domains. Sine and cosine, you can put any theta you want in. As big or as small as you want, so negative theta to theta, negative infinity to infinity. The tangent and the secant, if we think about the tangent's what? Y over x. Secant is r over x. So both of those have x's in the denominator. So wherever the x value is 0, and that would be up here at pi over 2, and down here at 3 pi over 2, are any coterminal angles with that. So negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, all of the multiples of odd pi's over 2's. So of course not 2 pi over 2 or 4 pi over 2, but 1 or 3 pi over 2's. Those would have to be eliminated. We could write that like this. Theta, the tangent and the secant have domains. Any theta such that theta is not equal to 2n plus 1, that will give us simply odd numbers. N being an integer will give us odd values, all the odd integers times pi over 2. All right, cosecant and cotangent. Cosecant, that's r, well, or 1 in our case, cosecant over y, and then cotangent, that's x over y. So again, these will be undefined when y is 0, and so y is 0 at the even halves of pi's. So that means at pi and at 2 pi. All right, so at all multiples of pi. So we could say you could use cosecant and cotangent for any angle such that that theta, that angle, is not equal to a multiple of pi. Okay. So now let's get to some actual problems where we're going to find the trig ratios of particular angles. Now, it would be helpful if you know where these angles are, right? So 7 pi over 6, it's going to be helpful if you know where that is. So figure out which quadrant you're in and what is the coterminal angle. If you want to think of that as, I think of it as degrees, but if you want to think of it as radians, the coterminal angle, or the reference angle, I guess, is really what I want to say there. And then we'll draw a triangle. So, okay, 7 pi over 6. 7 pi over 6 is right here. It's the same as 210 degrees. So we're going to draw a little triangle. And so something like this. And, you know, maybe you don't draw it perfectly to scale. The reference angle here is going to be 30 degrees or pi over 6. And so now I want to think about, okay, what are the parts of this triangle, right? So, so this is the, we can think of it as -1. We can think of this as 2. And we can think of this as negative square root of 3. Now, of course, doing this does not put it on the unit circle. If I wanted to do it on the unit circle, then I could draw it, and then I would have to call this 1. Then this would be -1/2, and then this would be negative square root of 3 over 2. Now, me personally, I don't care if you don't have to put this on the unit circle unless it specifically said use the unit circle. But the ratio, right? The cosine is the x over the r, right? X over r. So if I'm on the unit circle, then it's just the x. But if I'm not using the unit circle, it's the ratio of x over r. So either way, it's negative square root of 3 over 2, which I would get directly from just the x value if I was on the unit circle, negative square root of 3 over 2, or the square root of 3, which negative square root of 3, which is the x, divided by 2, which is the r. So it doesn't matter whether, as far as I'm concerned, whether you're using the unit circle or not. Just draw a triangle. Figure out what quadrant that angle is in. Draw your right triangle down or up to the x-axis. Label the sides of that right triangle. It's going to be one of our special right triangles. You can't do these without a calculator unless it's one of our common angles. So it's going to have a reference angle of 30, 60, 45, or it's going to be a it's going to end on one of our axes, okay? A quadrantal angle. All right, so do the same thing here. Tangent now. So the tangent of 3 pi over 4. So think about which quadrant you're in. 3 pi over 4 is up here. I'm going to draw a right triangle. I mean, you don't want to make this huge, but make the triangle big enough so that you can actually label this stuff. So I know my reference angle is 45. Anything ending in a 4, denominator of 4, is going to give me a reference angle of 45 degrees. We'll label this 1, negative 1, and square root of 2. But again, if this was a unit circle, then this would be 1. This would be 1 over square root of 2, 1 over square root of 2. All right, the tangent, I always think of this first as the y over the x. And so what is my y and my x? So this is just going to be negative 1. Okay. So like this one was much easier to do if I didn't use the unit circle. Coming up with the unit circle values, this would be 1, this would be square root of 2 over 2, this would be negative square root of 2 over 2. It just, it doesn't matter to me whether you're making your radius or your hypotenuse equal to 1, specifically putting it on the unit circle or not. Okay, next one. Why don't you pause the video and do the rest of these. Draw your right triangle, label it, and figure out what the ratio is. And then unpause the video to see me do the rest of these. All right, so C, negative 5 pi over 4. All right, so that's 1, 2, 3, 4, 5 pi over 4. So it's really the same location, same terminal angle as the last one, part B. So a reference angle of 45 again, 45 degrees, or pi over 4. Let's label this 1, negative 1, square root of 2. Secant, the secant is r over x. Now, of course, if you look up above in the notes, we know secant is 1 over x, but that's, again, only if we're on the unit circle. I did not set mine up as being on the unit circle. Okay, so the r, which is the square root of 2, over the x, which is negative 1. So we would just write this as negative square root of 2. Okay, secant 5 pi over 3. So think about where that is. That's 1/3 of pi, 2/3, 3/3, 4/3, 5/3 is down here. Reference angle 60 degrees. Sorry, I'm writing that really small. You can barely see that. 60 degrees. And so let's label the side. So I'm going to call this a 1, call the hypotenuse 2, square root of 3, but it's negative. Remember, if we include the negative signs, we don't have to use the all students take calculus to remember whether we should be positive or not. All right, sine is y over r. So now I just do, okay, this is negative square root of 3 over 2. Okay. E, we have 11 pi over 6. Again, it just helps if you know where these are. That's over here. Reference angle of 30 degrees. I'm not drawing it perfectly to scale. So this will be negative 1. This will be 2. This will be a square root of 3. Cotangent. Cotangent is x over y. And so x over y would be square root of 3 over negative 1, or we'll write that as negative square root of 3. All right, the next one, 3 pi over 2, that's down here. Now that's a quadrantal angle. So what you have to do with that is you can't draw a triangle. And some people kind of like, oh, let's draw a triangle over here, or that doesn't make any sense. Don't do that. We want to draw the hypotenuse from the vertex out to our point, and so the triangle sort of collapses down and it's just a segment. So with that, we want to think about what's the location of this point, and now it probably makes sense to go ahead and put it on the unit circle. So this will be 0, negative 1, and you might say with an r of 1. Okay, so we have, like, you know, a circle that goes around, but the point here, and again, you can make the circle as big or as small as you want, then, but why not just use the unit circle? It makes it the simplest. So cosecant is r over y. So we want, and then this is the x and the y and the r. So we have 1 over negative 1, which is negative 1. G, tangent of negative pi over 2. Well, where would that be? That would be just right over here. Going this way, though, ultimately. But the whole point is, what's the location of that point? That's negative 1, 0. And we have an r value of 1. So the tangent, remember, is y over x. And so we want the y, which is 0, over the x, which is negative 1. So this should be 0. All right, 7 pi over 4. That's in the fourth quadrant. It should be over here. Reference angle of 45, because, you know, it's a pi over 4, so it's 45. Gosh, you can hardly read. I read that so small you can barely read that, 45. So this will be a 1, a negative 1, and again, square root of 2. Not putting this on the unit circle, but you certainly could if you wanted. It just makes these a little bit more complicated. All right, cosine. Cosine is x over r. So this will be positive 1 over the square root of 2. Of course, we want to change that so that those are radical downstairs. So square root of 2 over 2. All right. On example number 2, it says, find the exact value of theta in the interval of 0 to 2 pi, where the angle is equal to square root of 3 over 2. So what we want to think about is we want to, you know, draw a picture, right? So sine of the angle is positive. What quadrants is sine positive? Well, we can certainly do, so we draw a triangle, right? Draw a triangle. May not be perfectly to scale. Think about sine. Sine is y over r. So we want to think about this as being the y, and that's the r. So the r is 2. The y is the square root of 3. In this case, we know this side is 1. And so what is that angle? Well, this is one of our special common angles. So this is going to be pi over 3, 60 degrees, or pi over 3. We want it in radians. They asked it for it in this range. That tells us we want our answer in radians. Now, that's a great answer, except it's not the full answer, right? It could also be up over here. Again, not drawing really that to scale very well. That looks like a reference angle of 45. But this would be negative 1. This would be square root of 3, and that would be 2. The sine is positive in the second quadrant as well, so it could be over here with also a reference angle of 60 degrees. And so we have pi over 3, but we also have 2 pi over 3. So pause this video and do these other 3 and see how you do with those. All right, tangent. I find it helpful to think about what tangent is. Tangent is y over the x. And so that's negative 1 or negative 1 over 1. So the 1 could be upstairs could be positive, or I could say what? I could make that 1 over -1 as well, right? The negative doesn't have to be in the numerator, it could be in the denominator. So tangent is negative. Which quadrants is tangent negative? So we know the tangent is negative in the second and third quadrants. So let's draw something in like this, and we have two triangles. I'm going to make it a little bigger. So we know we're in the second or fourth quadrant, second or fourth. Tangent is positive in the first and second. First and third. So we know we're in the second and fourth. All right, let's label our triangles using these. So we have a 1 and a 1, a 1 and a 1, but let's make sure that we have the negatives. -1, the x is negative here, the y is negative here. So now what would these angles be, right? They're both 45 degrees, but neither is actually 45, neither is pi over 4. It's that, that's the angle we're interested in. And then all the way around here, that's the angle we're interested in. So this is 3 pi over 4 and 7 pi over 4. Okay. The next one is cosine. Remember that the cosine is x over r. And think about where the cosine is negative. Cosine is negative in the second and third quadrants. So let's draw triangles. I'm just drawing generic ones. I'm not really drawing them to scale because I don't know what the reference angle is off the top of my head yet until I think about it some more. So the x and the r, so the r is 2 and 2, x is -1 for both of those. So this will be square root of 3 and negative square root of 3. Don't really need those, the y's, but that might help us visualize what that angle is. The reference angle in there is going to be 60 or pi over 3. But what is that angle? And then what is that angle down there? Like we know the reference angles, but what are the actual angles? So 2 pi over 3 is this first one. And then so we have 1, 2, 3, 4 pi over 3 is the second one. So put a comma between them and just box those in. All right, and then this one we want the cosecant. The cosecant, and we know the cosecant, well, that's r over y. Now this one might be a little bit easier to sort of unsimplify. So this is simplified, but could we also just say that's -2 over the square root of 3, right? In other words, divide top and bottom by square root of 3, essentially, right? And we could get back to this. So if we had this, we multiply top and bottom by square root of 3, we would get the simplified version. But we really want the unsimplified if we're going to label it. It just makes the triangle easier to visualize as one of our special right triangles. All right, cosecant, which is the reciprocal of sine, and that's negative. Where is sine negative? That's in the third and fourth quadrant. So draw a triangle, draw a triangle. And so we want the r to be -2, so the r can't be negative. So we really want this to be negative and that, of course, to be positive. So that's going to be 2 and 2, and negative square root of 3, negative square root of 3. So these reference angles are both pi over 3, which is 60 degrees. We can call this -1 and 1 if you want, but what are those angles? And so that's 4 pi over 3 to get down here. And then to get all the way over there, 5 pi over 3. Okay? So it helps, you got to know where that particular trig ratio is positive or negative, depending on the value, which quadrants we're in. Draw a triangle, label them given the information, given the ratio, label the sides of the triangle, figure out what the reference angle is, and then come up with the actual angle. All right, let's go on to page 2 now. So we're continuing our discussion of, on the back, we're going to talk about some more linear, or like rotation, kind of building on our ideas that we learned in the last section with arc length. But before we do that, let's approximate some values here. And so this, I think we're asked to use our calculators for this. So the sine of an angle is equal to this. Well, what we want to do is we want to do the inverse sine of 0.2748. And so we just ask our calculators to do that. Now you have to make sure that your calculator is in radians, right? So this is the ratio, but we want this, again, they told us the range is in terms of radians, 0 to pi over 2, so that's the first quadrant. All of these, we're going to get some kind of angle, theta, in the first quadrant. So make sure your calculator is in radians, and you just plug these into your calculator. So inverse, if the angle is equal to this ratio, then the inverse sine of the ratio gives us the theta. So the theta would be equal to something like 0.278. And if you want to say radians, just so that you overemphasize the fact that the answer is in radians. Don't have to put it, because by default, if you don't put degrees, it will be known to be radians. Okay. Next one. All right, so this one we're simply going to say theta is equal to the inverse tangent of 1.0790. Just plug that into our calculators, and we get a theta equal to 0.823, and that's just radians. So if you want to put radians. Okay. Now the next one's a little trickier because we don't have a secant button on our calculator. So first, let's think about what that would be as a cosine. So the cosine of theta, so if the sine of the secant of theta is this, the cosine would be 1 over that, 2.5312. And so what we can do is take the inverse cosine, so secant, and then cosine, the inverse cosine, and then put this in as this ratio, 1 divided by that. And that should give us something like 1.165. Again, that's in radians. And then the same thing for this one. We don't have a cosecant button, but we can say, well, the sine of the theta is equal to 1 divided by, not good to use slashes, but I've got little space here, 1.9685. So that whole thing, we could do the inverse sine of this ratio, and that will give us our theta. All right, so theta, in this case, 0.533 radians. Okay. All right, when using the inverse trig function on your calculator, the resulting angle measure will always be in this particular range. So if I use the inverse sine, now notice up here we only asked it for, to give you the answer in quadrant 1. And we restricted our values so that it was always just a positive radians. But this inverse sine always gives us an output from negative pi over 2 to pi over 2. And then for cosine, it's always 0. So let me draw a picture to help you visualize that. That means when I use the inverse sine, the angle I get will be negative pi over 2 to pi over 2. For cosine, then it's from 0 to pi. So it's in those two quadrants. And then for tangent, it's like a lot like sine. It's from negative pi over 2 to pi over 2. However, remember, we can't do the tangent of pi over 2 is undefined, so we don't include it. So these are square brackets, but these are parentheses, excluding negative pi over 2 to pi over 2. This idea will come into play more as we get into the trig chapters. Okay, now let's look at some linear versus angular velocity. Now, some of this is a little bit tricky because you've never really talked about angular velocity before. There is a video. I think I should have a video that talks about this. Oh, I think we already talked about this. Yeah, we talked about this the other day when I showed you the video with the two bugs on the record player rotating, and we talked about how they both are on the record and they're spinning at the same rate, so they both have the same angular velocity, but the bug on the head that has the bigger radius has the bigger linear velocity, even though they're traveling in a circle. They're not traveling in a line, but when we say linear velocity, we're talking about the length of the arc divided by time, and with angular velocity, we're talking about how much angle is being moved through with time. Okay, so linear speed, again, is the arc length, even though it's not a line, it's still an arc length, s divided by t. And then the angular velocity, we use that, here we use v for linear speed. For angular speed, we use something that looks like a W. We call it omega. It's a Greek letter. It's a W that have its sides kind of curved up a little bit more. Okay, so omega is just like velocity is distance over time. Angular velocity is angle divided by time. So how much rotation you've moved through in a set amount of time. And of course, with all of these, like we saw in the last section with arc length and area, everything's got to be, theta must be in terms of radians. So it's radians per time, really, instead of just units per time. All right, so let's look at number 4. Suppose that point P on the circle, so point P, look at this drawing up here maybe, on a circle with radius 12 inches, and ray OP, O being the vertex, right? The 0 point P, that ray is rotating with an angular speed or angular velocity. The difference between speed and velocity just means sometimes speed is a magnitude, rather it's not telling you which direction it's going in. So speed would just be a magnitude. Maybe it's rotating to the left. Maybe it's rotating negative. Maybe it's rotating to up. Maybe it's rotating down. But speed would mean like we don't really care which direction it's rotating in. Okay. So the angular speed is pi over 12 radians per second. Okay. So they've given us an angular velocity. That's omega. And they've given us this up here, that's the radius. So they want us to find the angle generated by that ray OP, I guess it should be ray OP, in 10 seconds. So if we think about omega, well, we know omega is theta over t. We could rewrite that. Theta equals omega times t. And we were given that is omega, that we were given to that as pi over 12 radians per second. Now, I told you before that radians are dimensionless, but sometimes we'll use them sort of as a placeholder. We want to say that it's pi over 12 radians per second. We just don't want to say pi over 12 per second would be weird. So we put the radians in sort of when we makes kind of more sense to put them in, but often we don't have to put them in. All right. So we want to know the angle generated, right? So we are going to take this and solve it for theta. We know omega and we know time. All right, so omega, that we know is pi over 12. And let's keep the units in, because the units are kind of important, because sometimes they can give us different units. And if you're not keeping track of those, you won't know if you have to do dimensional analysis. So we have radians per second is what they gave it to us as, right? Radians per second up there. So that's omega times our time, which was 10 seconds. So if they had said like 1 minute, then we would need to convert. But here, the seconds upstairs cancels with the seconds downstairs. And we can see that our answer will be in radians because that's all that's left. All right, so when we simplify this, we could reduce the 12 and the 10, 5 and 6. So this will be 5 pi over 6. And I could just leave it as 5 pi over 6. If you want it to include the term radian, the units radians, that's fine too. But 5 pi over 6. Here we don't really need the radians. Here it's kind of nice to include them because otherwise it's like nothing over seconds per second. And it just seems weird. All right, let's look at B then. Find the distance traveled by P along the circle in 10 seconds. Now they gave us R up here and we haven't used it yet, but we will need it here. So find the distance traveled by P along the circle in 10 seconds. So that is the distance. That means the distance that is the arc length, right? And so we want to find that arc length, and we know that we can look at velocity is equal to arc length over t, right? That's this, velocity, linear velocity. And so we want to just rearrange that. S is equal to v times t, this v being linear velocity, and this t being time. Now, we have a formula for velocity. Velocity, remember, is going to depend on r, so we could take out the v, and use radius times omega times t. All right, and do we know the radius? Yes. Do we know the angular velocity? Yes, they gave that to us up here, up above there. And we do know the time? Yes, 10 seconds. So we simply plug everything in. So part of it is just taking our formulas and making sure that we can, we have everything we need and to do substitutions into our formulas. So that's part of the battle. You just got to be comfortable with these formulas up here, and as well as this one, the velocity, linear velocity is equal to radius times omega, the angular velocity. All right, and so let's plug that in. So we have 12 inches is the radius. And again, you keep your units here. Omega, in this case, is pi over 12 radians per second. And then 10 seconds is the time. And so you could see seconds are going to cancel with seconds. 12 will cancel with the 12. And so it looks like our answer should be what? 10 pi. 10 pi. And then what is the units? Inches. We have units, so we don't really include the radians. We could say 10 inches radians, but radians, remember, are sort of dimensionless. We're not really going to use them unless we sort of have to. So it makes more sense to just say 10 pi inches is the length that we traveled. All right, now it says find the linear speed of point P in inches per second. So that's velocity equals s over t. We could just use this formula here too. If we're asking to find the linear speed of point P, we could use this formula as well, r omega. We know both of those, but we also know s and t. Do it that way if you want, but it will give you the same answer. So s is what we calculated up above. That's 10 pi inches. And then we want our time that occurred in was 10 seconds. That corresponded with that. And so that's just pi, and the units are inches per second. Let's go ahead and do that with our other formula, r omega. So that was 12 inches pi over 12. And that was, let's see, this one is inches, and this one is This is radians per second. And so you can see we get the same thing. We get pi inches over seconds. So you get the same answer if you use that formula versus if you just use that formula. Okay, and the last one, number 5. A belt runs a pulley of radius 5 inches. So the radius here is 5 inches. At 120 revolutions per minute. So whenever you see RPMs, know for sure that that is not radians. That R for RPMs is revolutions per minute. It's like 44 RPM is 45 RPMs was a standard rotation rate on record player. So RPM, the R does not stand for radians. It universally, everyone knows, it stands for revolutions per minute. So when you see that on a test, do not think that's radians, it's revolutions. All right, so we're given, what are these things? This is the radius, right? So this is R, and the revolutions, that's omega, that's angular velocity. It's revolutions per minute, it's rotation per minute, but we're going to have to convert that because we know we have to have radians, so we're going to have to convert that. Find the angular speed of the pulley in radians per second. So that's what this was. They gave us omega equals 120 revolutions per minute. We want to convert that to radians per second, so we need to do some dimensional analysis. Let's get rid of the revolutions first. How many revolutions and how many radians? Well, we want revolutions down below so that they cancel with the revolutions up above. So that means 1 revolution, well, that's 2 pi radians. And then we want to change minutes to seconds. So the minutes are downstairs, so I need minutes upstairs. 1 minute is 60 seconds. And so my minutes cancels with my minutes. My revolutions cancels with my revolutions. I'm left with radians per second. We just want to reduce this wherever we can. Let's see, 60 and 120, that's 2 and 1. So that looks like 2 times 2 pi, that's 4 pi. And again, this time we're going to use the radians in the units, radians per second. Okay? And because it doesn't make sense to say 4 pi and then per second. We'll say radians per second. When there's nothing else there, we'll put the radians in. All right, find the linear speed of the belt. So how fast is this thing moving as linear speed, or what's the arc length divided by time, right? So we want V. So V is equal to S over T. But V is also equal to R omega. We already have our omega up above with the correct units. We have to have it in radians. So it seems like that would be the one we would use. So the velocity is equal to the radius. That gave it to us as 5 inches. And omega is 4 pi radians per second. And so that should just be 20 pi inches per second. Again, we don't say radians inches. Since we have another unit, we just say inches per second, and we ignore the radians entirely. Okay. All right, so again, make sure that you know these formulas. We need to know V equals S over T. We need to know omega equals theta over T. And then also this one we use a lot, the linear velocity is R times omega. Omega and theta must be in radians. Doesn't have to be in per seconds. It depends what the units of time are. But the angles cannot be in degrees. They must be in radians. And so must omega, radians per unit of time. Okay, here is your homework down here. Due next class. Remember the times 4, multiples of 4. E stands for even. Okay.